I'm going to give you an overview. I've worked for quite a while at first at NWP and then at DWD, always on the physics, and I really enjoy this this part because it's modeling. It's a little bit like playing like a child on a toy. So I'll try to give you an overview, and I'm happy to answer some questions if they come, or at the end as you want to. So let's see how we progress. Okay. So I want to give you an overview. I want to tell you what parameterization is and what kind of parameterization are there and why we need them, and give you a little bit of a theoretical overview, but also how the parameterizations are, or which parameterizations are available in ICANN. So first of all, the problem is massive. You have clouds and convection and things on all kind of scales, from the 1,000-kilometer scale storms to the very small scale. So it's huge. We have to describe that. You've already heard a little bit about the non-hydrostatic equations, the dynamics, so we have terms that will add on these that describe the physical small-scale components. And one key idea of that is the Reynolds averaging. You can see that here in the middle. Here. So basically, you have a quantity on the very local scale, and you can divide it up in a mean over a grid box, or sometimes we call that filter scale, and then you have a perturbation of the parameter. And while the grid scale will do the dynamics on this mean quantity, the smaller scales are in the prime quantity, in the phi prime. And if you then add transports, you will have second order terms. You will have W prime times temperature prime, and so on. You have momentum transports, and these second order terms will then sometimes be described by third order terms. So it becomes easily quite complicated, but this is basically the problem that we have to deal with. So if you divide it up in some kind of grid, this is a very rough grid, for example. And then you can already see that in each grid, there's still a lot of variability. And if you make that grid smaller to, let's say, 10 kilometer, you will still see a lot of small-scale detail that is in the middle, which we are going to have to describe. Now, the things become even worse because this grid you've seen is actually good, but the resolved grid by the dynamics is even worse. So if you look at a power spectra of a numerical model, here's a little bit of a diagram, schematic. So basically, you have your resolved scale. Well, the resolution goes all the way to this line here, but in most models, the power is damped at these very small scales, and the ICANN model has a effective resolution of maybe 7 times delta x. So it looks like here you have another example of the model where you can see the power scales. So you have typically a k to the minus third law. If you go to the convective scale, you expect a flatter power law k to the minus 5/3, but we hardly get to that scale if we are at 10 kilometer or maybe even at 2 kilometer. Because imagine that you're at 2 kilometer resolution, so 7 times, so you might only have an effective resolution of 14 kilometers. So that makes matters worse. Here's another example, a third example of a power power spectrum. And I think that's also quite interesting. So if you do look at the 2 kilometer scale, there's a difference between the power law at nighttime and at daytime. So at nighttime, on the left side, it's still a little bit calm. But at daytime, you have convective events, and they are probably contributing to this bump that is being created here at these scales. Now, the model seems to try to mix convection at these larger scales, so it propagates them to maybe a little bit too large scale. So if you remember the last figure, so you have now a grid that's 7 times worse. So so the parameterization have to do a lot, and the parameterizations will describe these phenomena at the 10 kilometer and smaller. And I just wanted to show a little bit like what kind of scales are around there. Of course, you know, these large scales like monsoon, cyclones, they are resolved. And I think weather forecasting became maybe popular in the 80s or 90s. And at that time, the resolution was maybe 80 kilometers. And I think the big success of them comes from the fact that the baroclinic instability lives on scales that are maybe 5,000 kilometers size. So these storms that come over the mid-latitudes and dominate our weather, and particularly winter. And I think if you have then a model that resolves about 100 kilometer, you can describe quite well these storms, these extratropical storms that come through, and I think weather forecasting was quite good. And then later, in maybe 10 years ago, people were able to go all the way to 2 kilometer over regions. Now, NWP doesn't really exist globally at 2 kilometer yet. The best models are at 9 kilometer globally. So you're still far away. But when you get then you made that improvement to go to 2 kilometer for the local area models, and you now have them over any country, most countries that. Or many countries, you imagine. So then you get to a little bit to that convective scale that is a completely different phenomena. So now the convection lives at maybe a few hundred meters or maybe a kilometer. And so these models that are at 2 kilometer, at 1 kilometer, maybe at 500 meters, maybe even at 300 meters, they will have trouble to do that, but they also have success. So there's all kinds of models that are around that deal with these different resolutions. I told you about the global models for NWP that live in the 1 kilometer to 1 kilometer, 100 kilometer region. Climate models have to go for a fairly low resolution, particularly if you run for 1,000 years. If you want to look at high resolution, the large eddy simulations have been a very popular research tool over many years, and I've used them too. And I've actually used the ICAN model as a large eddy simulation model at resolution down to 72 meters. I looked at Australia. There's Hector, the convector, massive convective, the biggest convective event in the world. Lives on an island there. If you want to go to even higher resolution, there is the direct numerical simulation that you can look at centimeter scale simulations. So, for example, if you're interested in a very small phenomena, the entrainment on top of stratus clouds, that happens in maybe just a meter or so. And if you want to resolve that, then you need ENS. So the system is a little bit fractal, or let's say it lives on all scales down to the millimeters. And how do we do it? So here's a nice picture of the parameterizations, the typical parameterizations. The picture is from NWP. But it's generally true that these are the parameterizations that we have in our model. And I think we filled on some of the things that are added on this figure. So basically, what you have is you have solar radiation coming in, short-wave radiation coming in. The orange line. That warms up the surface. Then you have turbulent diffusion on the surface that transports heat up. You have then condensation. So you have clouds, you have shallow cumulus, deep convection, and you introduce waves. And these gravity waves, they can live on fairly small scales. So some of them are, kilometer scales big. They're resolved, and some of them we have to parameterize them. Which one did you forget? We have aerosol chemistry. We have the ocean now. We have waves on top of the ocean, which are also very important because that makes the roughness length and changes the winds, but also is very important for the ocean mixing. And you have the surface. Oh, that's a big one. You will get a lecture on that one. Lakes. We have a special expert at our place at Dimitri Miranov, who's an expert on lakes. Okay, so that's an overview, so then can finish, but I will give you a tiny more little detail. And then we have some lectures, for example, after me, Mirjana on radiation. Urban areas, yeah. So the requirements, the basic requirements for parameterizations. I think one of the key things is that you want to have your parameterization general enough that it works for all kinds of applications: global, limited area, environmental forecast, climate prediction, research. But it also works seamlessly for all the resolutions that we want to cover. So our icon model really works for resolutions from, let's say, 80 kilometers. For climate, 2 kilometers for regional, and even 100 meters for LES. And we just have to change nameless parameters to switch from one application to the next. There is a few different parameterizations that we might have to turn on and turn off for a particular application. So you want to have a general seamless set of parameterizations. And yeah, there's one thing that is also worth pointing out. I feel like it would be best to have a set of parameterizations that know each other and that work well together with each other. So if you have just boxes and then you have an interface and the others have no idea about them, is not so good. For example, you have convection, and then you retrieve some water from that, and then you go into microphysics and cloud, and that feels radiation. So the interactions are very important. Yeah, final cycle, clouds, windcasts, data simulation is also important. Okay, so we started a project to make our model seamlessly work on different scales. Now, the icon model was developed for NWP originally. Maybe it became, I think it became operational in 2015 in February or so. And the primary idea was not really to cover the whole range of applications from LES to climate. But in the early 2020s, we decided to go to an endeavor, and there were maybe 10 people working for a few years on that subject, to add an open to it, so that we then will be able to cover the longer timescales. You need to have sea ice and yeah, all the interactions. It's a hard subject, yeah. But with that, now we have a seamless model. And I think we could have also used the word unified, but that's already taken from the Meta Office. Seamless is basically the same thing. And here I'm showing you a little bit these applications that cover these scales. So on the left-hand side, you can see our 2-kilometer weather forecasting model over the German region. And you can see the model covers the observations quite nicely in this particular example. So it can describe these little storms that can also describe fronts. Eurolast, they are very long, but they are very thin. They're thin, maybe 10 kilometers, so to resolve them is not easy. In the middle, I'm showing you our NWP system on the 7-day scale, so where we forecast with an ensemble at 26 kilometers into the 7-day forecast, and we also have one member with 13 kilometers. And on the right side, I'm showing you the seasonal forecasts, where we give an outlook to the next 3 to 6 months, and see how warm than normal or cold than normal that is. This figure here looks quite nice. The figures I see often are always red. So basically, the next 3 months are forecasted to be warmer than normal, but that relates to the reference. So if you have a reference in the 90s, then any seasonal forecast you do now will be warmer than normal. It will be just red all over. But this is probably a more recent reference, so you can see, okay, that's colder than current normal, yeah? And on the bottom, you can see climate change here. So with that, I want to go into a little bit more the details of the parameterizations that are available in the icon. There's radiation parameterizations. We do want to point out that you should use the ECRAT, which you will hear right after me. Non-logarithmic gravity wave track. We have also the subgrid scale orography, clouds, the microphysics, convection, turbulence, and land. So I will show you a little bit here how they are interacting with each other and how they are called in the in our icon model. And you can see here this flow of parameterizations and also dynamics and how they're called in the model. I think that is quite nice. Yeah, so So the coupling is performed at constant density. The physics parameterizations work on mass points. And the conversion between the set of thermodynamic variables is reversible. And I think I'll maybe show you this a little bit more detailed here. So you have what we call fast physics and slow physics. So the fast physics are the physics packages that have shorter timescales. So we do need to update them on the advection time step, which can be on the order 100 seconds or so. And you can see this loop here, the red loop, the faster one. There you have fast physics, which basically is the surface model, the soil and those things. We have the saturation adjustment, which is called right after that. I'll come to that. Then the lakes and sea ice, turbulent diffusion, microphysics, and then we call a second time the saturation adjustment. Just for now, the saturation adjustment ensures the equilibrium between water vapor and cloud liquid droplets while changing the temperature. And that is a critical parameterization that you have to make that adjustment maybe multiple times, 2 times in this case. And then comes the slow physics. Now there's some physics like radiation that act on a slower time scale. So if you have a heating rate of maybe 2 Kelvin per day, so that comes from the radiation. So it's not so urgently to change that all the time. And it's also very expensive. So we have some parameterizations which are then just called once in a while. So we set a time scale, let's say 500 seconds or even half an hour for different times, for different of these convections. And then at the time when we say, okay, the 600 seconds are over, we call convection and it produces a tendency. And this tendency will live for the next 600 seconds. And we'll just add every time step a little bit of that tendency. So this is the there's a few usual time steps for these parameterizations. Yeah, I can set them in a detailed way. Yeah. Okay. So a few more details. One detail is, I will show the model is very expensive. The parameterizations are very expensive. So to make things a little bit more efficient, we decided to not calculate the moist physics in areas in the stratosphere where there's hardly any moisture. We do propagate water vapor, but we will just turn off the moisture physics in those regions. You can set that as a name limit parameter. We set it to 22.5 kilometers. And now I'm going to show you 2 slides on each of these parameterizations that are in this model. So, but do you have first a question about generally about parameterization and how the model goes through them and why we do have them or how many of you have developed a physical parameterization in a model? Worked on it more. Yeah. Those for you. Which one? Which parameterization did you work on? Yeah.
The room freezing.
Okay. Microphysics. Yeah. Okay. And what about you?
Lakes, aerosols, cloud
in
a climate.
Oh, okay. Nice, yeah. Yeah, so it's kind of interesting that we have this. I think it's kind of an interesting idea that developers in the 80s or 70s came up with this idea to put the physics into multiple things like convection and all the other ones, turbulence, and then went on to very, very detailed parameterizations of all that. And when we say physics, that's also a bit of a funny thing, because the Navier-Stokes equations is also physics, but we just have that jargon that these moist things or these small scales, we call them physics. But one more interesting point, I think, in general, before I go to that, is that we now, of course, are beyond the 70s. Very famous convective parameterization was developed in 1974 by Arakawa and Schubert. But now we are in the 2020s, and obviously we have machine learning models on one side, and then we have physics-based models on the other side. And I think we have to rethink ourselves, maybe a little bit like our brain, but that's another one. So we have to kind of rethink, is it the right approach that we have went into in the 70s? We went into this lane, parameterizations, split the model up into pieces, and then describe it as good as we can. And if you look at the parameterizations today, you will see that there's a lot of hand waving in them. Physics is almost a compliment. Because convection, you say, okay, well, this thing is going up, and then you have this little entrainment on the side and so on. It's a lot of hand waving. But there is an idea that we could use the physical description together with a machine learning description. As, for example, ideas that we have a nudging simulation from the machine learning model, but the physics model running to describe all the details. Now, if I want to know the falling of ice crystals or writing or whatever, you have it in the model. You can just make a print statement and you know it. You don't have that luxury in a machine learning model. But for that philosophy, I go to these parameterizations, and the radiation is the first one I mentioned when I showed you the figure, because of the sunlight coming down.
It's curious. So you said maybe we have to rethink this separation, but you didn't say what your alternative would be. So
I don't know a good alternative of it. But one thing that should always be high up to unify parameterizations. So there have been some ideas to unify, for example, turbulence, convection, and clouds in one parameterization, like higher order turbulence schemes that can treat convection. And Larsen is one paper. And they have even tried to add microphysics into that package too. So have one package to describe all moist physics. I think that that's certainly one way to go to. Also, one way to go to is to run large eddy simulations, maybe on a large scale, maybe globally. Maybe we can do that with big computers. In large eddy simulations, you don't need a complicated turbulence parameterization. You don't need a convective parameterization because you resolve it. An idea would be to run this very high resolution physics model for just maybe a few days over the whole globe, and use that for learning So that's another idea that is in the room. Okay, so radiation. Now I'm showing you for each of these spermizations the tendency in temperature that is being coming out of the spermization. This is coming out shortwave and long wave. So shortwave is the radiation that comes from the sun, and long wave is the radiation that comes from the Earth. Now, not so nice about this picture is that you can see the upper levels, the stratosphere here massively. So there is a very strong balance between a warming in the ozone layer and cooling in that ozone layer in the upper levels. And you can see that, maybe that's 10, 20 Kelvin per day cooling and warming. But I'm not so interested in that. I'm more interested in the lower parts. And there is very little warming of the sunlight in the atmosphere because the sunlight goes mostly through the atmosphere with a few absorption by droplets or other things. But the key thing there is the cooling from the long wave radiation. So you have a warm, moist air in the troposphere, and that radiates heat out to space. So you have in the whole troposphere typically a 2 Kelvin per day cooling rate. And that drives convection. So remember the 2 Kelvin cooling rate from long wave radiation. Yeah, so next is the convective polarization. And you see the details. So this is kind of more the summer deep convective events that we do not have today. Because then you would have sunshine in between, which you can see. Now, the things you have, the first thing you have to do is you have to decide what kind of convection you have. So you do have more shallow convection, or do you have deep convection? One of the distinctions between two might be shallow convection is just nice, it doesn't rain. The deep convection goes higher up and produces masses of rain, and that has a lot of impacts on it. So if you do have convection, you have a big updraft, and that's very important. But what people forget is that the heating, the main heating that comes from the convection is from the cumulus-induced subsidence. So you can see these orange lines. So what comes up must come down. This subsidence brings warm air from the higher levels to the lower levels, and it produces the warming. That's the main impact of convection. And I'll show you a figure of that. Precipitation is very important. Yeah, a lot of things. The precipitation then also produces downdrafts. So you have precipitation that can be either inside the updraft or it can come down beside. And so that produces cooling of droplets and then even further downdrafts. Okay, so we'll go to the next one. So here you can see that cumulus-induced subsidence warming. And this warming is actually the same 2 degree warming per day than the cooling from long wave radiation. Then turbulence, look at one more detail here. You can see this warming in red, but you can also see that cooling near the lower levels, in the lowest kilometer. And that is partly from downdrafts that cool this area, but also from the transport of heat upwards. And this cooling, this blue, is exactly the opposite, as you can see here in the turbulence transports. So the turbulence produces a heating in the lowest kilometer in the boundary layer. And where does it come from? Well, the sun heats the surface, and it produces an instability close to the surface, and the boundary layer transport this heat up into the boundary layer. Then it's being taken up in convection, and that relates with the radiation. So that's the basic way it works. Now, quickly on the orographic and non-orographic gravity wave parameterizations. They're also very important, and they have a large impact on the scores in the model. And we describe them separately. So you have to describe the orography. And the orography will then produce gravity waves that propagate all the way up. And second, you can have blocking. So for the lower levels, you can have winds that go around the mountains. So we describe that as well. And then there's also other sources beside the mountains of gravity waves. So that can be storms that have produced variabilities or convection. And they are created, let's say, in the upper troposphere. And these waves, they propagate all the way into the stratosphere. And they have a large impact on this temperatures in the stratosphere. You can see that here. So the gravity wave, the non-orographic gravity wave drag has large impacts in the temperature and the winds in the stratosphere. And the subgrid scale orography mostly has an impact near the surface. Cloud cover predicts in advance, I can predict in advance mean quantities. So water vapor, liquid water, ice, rain, snow, graupel, and hail, depending on the microphysics package. Turbulence calculates a temporary cloud cover, but we need a cloud cover on the subgrid scale. That is very important for the radiation, because radiation impacts a lot of it. Okay. So here, one more thing, the microphysics impact. So there's a bit of a smaller impact on the temperature from the microphysics, latent heating and latent cooling, and the cloud cover. Yeah, so I think with that, I want to show you the cost of these parameterizations, which is massive, and the biggest one is the radiation, costs the most. Turbulence comes as the next one, and convection right after that. And so with that, I want to finish. So there's a huge variety of physical processes in the atmosphere, which act on different temporal and spatial scales. And there's different approaches that are followed, and we have, unfortunately, different packages that deal with these parameterizations, and you will hear a little bit more detail on some of these parameterizations after me. So with that, thank you, and I hope for some more questions.